see you all a bit later on. A big hand for Chris to start off with flying across the
Thank you, James. So it's really nice to be here. I used to live in Melbourne. It's a nice place to come back to. As James said, I want to tell you all about work that I do. So I'm an astronomer at a place called the International Centre for Radio Astronomy Research. I don't actually do any radio astronomy. I work with big computers. And what I work on is trying to understand how the universe formed, why the universe is the way it is. And so I use big computers, supercomputers, to build model galaxies and to look at how galaxies interact with each other. So this picture here is actually an image from one of the models that I run, or a simulation that I run. So this is showing two galaxies interacting. This is actually the Milky Way, our galaxy, and the next biggest galaxy to us, the Andromeda galaxy, and this is what's going to happen in a few billion years' time. So based on what we know about the Milky Way and the Andromeda galaxy at the present day, we know that in a few billion years' time there'll actually be a big collision between them. There'll be a big smash, and Andromeda and the Milky Way will smash together and they'll form a new galaxy. So it's quite an exciting thing to do, and we can do these kinds of experiments using big supercomputers. We can try and predict what the future is. So first of all, who can tell me about a supercomputer? Who knows what a supercomputer is? This is a picture of one. Yeah? It's the type of what?
It's like the smartest computers in the world.
So it's a pretty smart computer, and do you know why it's so smart? Does anybody know why it's so smart? Do you know?
I forgot.
Okay, well, listen, I've got to give these balls out, so do you want to try and catch it? Here you go. So the reason it's so smart is because it's like it's like the computer you probably have at home. Well, maybe you don't have a computer on a desktop, but you've got a little laptop or you've got an iPad. And instead of just a single iPad, it's like having thousands and thousands of iPads connected together. And so whereas with your iPad, you might type something in and it might take a minute or two to do it, if we run it on a supercomputer, we can do it in a fraction of a second. Now, why that's so impressive is because it allows us to do lots and lots of very detailed calculations. So when we want to try and work out an equation, we will have done it at school, say, we can sit down with pen and paper and we can work it out. And quite often you can take that equation and put it into a computer. And if you did that on your desktop computer or your iPad at home, it might take some of the things that we do, it might take a day to do, whereas in a supercomputer, we can do it in a fraction of a second. So supercomputers are extremely powerful. And the reason they're so powerful, because they're so powerful, it turns out that it's a very useful tool to have. So we're used to dealing with the results from supercomputers all the time. So for example, when you look at the weather on the news in the evening and it's telling you what the weather will be for the next few days, that's based on measurements that have been taken all around, say, Australia and New Zealand up here, and they've been fed into a supercomputer, and the supercomputer's gone away and crunched lots of equations, and it's predicted what the weather will do in a few days' time. So that's an example, weather prediction. Another example is what we might have done tens of years ago using big wind tunnels. We would have built a big wind tunnel and we'd have pushed wind through it and looked at how the wind passed over a car. But instead of building a big physical wind tunnel these days, we actually build a model of the car and the passage of wind in a computer, and we can understand how the wind flows over a car. And so this actually helps us make very fuel efficient cars because we can adapt the shape of the car so the air will flow over it more easily and we don't use as much fuel to get around. So these are very practical applications of supercomputing. So for example, weather prediction or making very nice cars or aeroplanes. But one of the cool things about supercomputers is that we can start to answer questions that we couldn't have dreamt of only a few decades ago. So a couple of examples. Who knows what DNA is? Well, I'll ask somebody else. Do you know what it is? What is it?
It's in the tiny bit inside cells.
Yeah, it's in your cells, and that's why we have the traits that we have. Here you go. So one of the cool things with supercomputers is that we couldn't have done this a long time ago, but within our cells there's this DNA, and these are very long strands of information. And using supercomputers, we've been able to map what's in the DNA, and that's been able to tell us what are in these genes, what's in this DNA, and how these are sequenced. So there might be billions and billions of these things in our body, but we can actually figure it out using a supercomputer. We can sequence it. The other thing we can do with a supercomputer is try and build a human brain. So that's something that people are trying to do in Switzerland at the moment. So they're trying to replicate what's in our head, the brain, and all the billions of connections between the neurons in our brain. They're trying to build that into a supercomputer. So that's something that's pretty cool, I think. So these are quite far out scientific blue skies ideas, people trying to understand why humans are the way they are by sequencing the genome, or looking at DNA in our bodies, or by trying to mimic what happens when we build a brain. How does the brain work? That's what they're trying to do. Whereas the kind of thing that I'm interested in is trying to understand how something like this forms. So this is a nice spiral galaxy. It's a picture taken with the Hubble Space Telescope. And you can see it's a spiral galaxy because it's quite flattened, but you see these nice spiral arms. So maybe later on, if the sky clears, we might be able to see something that looks like this. It probably won't be as pretty as this. So this is a real galaxy. But we can go and use these powerful supercomputers to try and build model galaxies and try and build them from the Big Bang, from the point of the Big Bang onwards. And so this is an example of galaxies. These are galaxies that have formed in a very big supercomputer simulation. So this computer simulation took about 5,000 years to run if we ran it on a desktop computer. Instead, it's only taken a few years to run on a very powerful supercomputer in America. And so we can see different examples of galaxies. So these are disk galaxies, flattened galaxies, and we can see these spiral arms that are very similar to the one that we saw earlier. Up there, they're elliptical galaxies, so they're just big balls of stars, very featureless. And these things here are the runts of the family. They're irregulars. They don't really look like one or the other. But we can do this in a supercomputer. And the reason we can do this is because of something called gravity. So does anybody know who this person up here is? There. Begins with an N. Newton. Yep. So does anybody know why Newton's so famous? Well, he's famous for lots of reasons. Well, that's one of the things he came up with. So Newton came up with this, what he called the universal theory of gravity. Does anybody know what the relationship between Newton and apples is? Well, that's true. I'll give you a ball anyway. But does anybody know what the connection between Newton and apples is? Do you know? Did you say he saw an apple falling from the tree? Yes. Okay. Oh, sorry. So we think it's probably a legend. We don't think it actually happened. But the story is that one day there was a big plague in England at the time, and Newton at the time was at college in Cambridge, a very famous university in England. And because it had shut down because of this disease that was sweeping through the country, he went back to his manor house out in the countryside, and he was sitting down and he was looking at the moon, and he was wondering, why does the moon not fall to the earth? Why does it keep orbiting the earth? And then the idea was that he was sitting under a tree, and all of a sudden an apple fell, and he saw the connection between the two. In his brain there was a moment of genius, and he said, aha, there must be this universal force. So the reason that the apple falls towards the earth is much the same reason that the moon orbits the earth. It's this thing called gravity. So Newton was able to go away, and I've talked a lot about equations. And equations are the way scientists try to understand nature. And so what Newton did was he said, well, there must be some universal force that's attracting the moon to the earth and also the apple to the earth. And he wrote this equation down up here. So you can see this equation F, which means force, is equal to this G here. This is something that we call the universal constant of gravity, or gravitation. And then we can see these three numbers, or these three letters here, M1, M2, and R squared. M1 and M2 are the masses of two objects. So for example, do you know how heavy you are?
29 kilos.
Okay, that's fine. Do you know how heavy I am? Only slightly heavier. Okay. And so the idea is that because you've got a weight and I've got a weight, gravity acts between us our two weights, and I get pulled towards you and you get pulled towards me. But if I move further away from you, the force of gravity weakens. Okay? So if we look at this equation up here, it's telling us M1 and M2 are our two weights, and so they multiply together, and the bigger your weight, the bigger the force of gravity. But this R on the bottom line, if I make that bigger and bigger and bigger, if I have a big number on the bottom and I make it bigger and bigger and bigger, that whole number there gets smaller, so the force goes down. And so this tells us something very interesting. And so Newton was able to say, well, there's this universal force of gravity. If I have two planets, the further apart they are, the weaker the force of gravity. The bigger the planets are, the stronger the force of gravity. And so this is a way that we can try and quantify what's going on. So we can write down this equation, and based on this equation, we can start to work out lots of interesting things. So in the years after Newton discovered this very, very famous equation, people started to apply it to things like the Earth and Moon system. So here's the Moon over here, and it orbits the Earth every how many days? Does anybody know? Anybody else? Anyone else? Okay, you? Yeah, it's about 28 days. So it takes about a month for the Moon to go around the Earth. And so it turns out that for this particular problem, where we have, say, the Moon and the Earth, we can solve this equation using pen and paper. And you can go through lots of equations, and you end up with something like this. So this is actually a picture of a blackboard, and we were working out how to do this. And you can see there are different cases, but there are lots of letters here that just correspond to things like distance and gravity and mass, things that dictate how long something like the Moon will take to go around the Earth. So it turns out that in this case, what we call the two-body problem, we can actually go away and write down some equations on a bit of paper and work it all out. What about the three-body problem? So you can see I'm just adding things on now. So here's the Earth and the Moon, and the Earth will go around the Sun every how many days? How long? Yep. So it takes a year. It takes a year for the Earth to go around the Sun. But it turns out that it's actually pretty tricky to solve this with pen and paper. We have these equations. We have this equation up here, but it becomes very chaotic when we try to work out what the solution is. We can't come up with a nice equation on a bit of paper. And this is quite interesting because we have a solar system of 8 planets. When I was growing up, it was 9 planets. Who knows which planet disappeared a few years ago? Yep. Pluto. Which, you back there? Pluto, yeah. So there are 8 planets in the solar system. You have the rocky planets in here: Mercury, Venus, Earth, Mars. You've got the gas giants out here: Jupiter, Saturn, Uranus, Neptune. And you've got the Sun here. Now it turns out we don't actually know if the solar system is stable. We're not able to write down equations that tell us what the solutions to the orbits of the planets are. We don't know whether the solar system will disintegrate at some point. So we know that the solar system has been around for about 5 billion years at this point, but we don't know whether it'll exist for another 5 billion years. It can become quite chaotic. So this is something that's taxed people for a long time, and we still don't know the answer. Even though we've got very powerful computers, we still don't know the answer to this. So this, we said here, we have the two-body problem. We have the three-body problem. This might be the 9-body problem because we've got the Sun and these 8 planets here. And we can see that it's getting very difficult to try and work it out. Sorry, you got a question there?
Yeah, how does Mercury get sucked towards the Sun?
Well, it's because of it's orbiting around. So although it wants to get driven towards the Sun because gravity is acting to pull it towards the Sun, it's also got motion. So it's moving sufficiently rapidly, so that will cancel it out, the effect of the gravity. Yeah?
Well, if the biggest sun multi-universe exploded,
Sorry?
the biggest sun multi-universe exploded, would it take up the whole multi-universe?
No. No. So you can have very massive stars. We'll talk about that later on, actually, because we'll talk about what happens when stars die in galaxies. So I said we had 2 bodies if it's the Sun and it's the Moon and the Earth. We have 3 bodies if it's the Sun, the Earth, and the Moon. We have 9 bodies if it's the Sun plus the 8 planets. What happens when we go to a galaxy? Who knows how many stars are in a galaxy? Roughly. Is it tens or hundreds or thousands? Or is it bigger than that? Do you know the answer? Did you just say 10 billion? Okay, that's the right answer. So there's about 10 billion stars in a galaxy. And so 10 billion is a big number, and we don't want to have to keep saying 10 billion and 1, 10 billion and 2, 10 billion and 3. We're pretty lazy. scientists in general are pretty lazy. We like to be able to do things very easily. So we just say, well, we'll call it Nbodies. So we get onto the problem of the Nbody problem. So n can be any number, but it's normally a very large number. And we can see that if we couldn't solve it for 3 bodies or 9 bodies, we certainly can't solve it for n, where n is some extremely large number, billions and billions or trillions. And so when we get onto this problem, we actually need to use supercomputers to do this, because we have to solve equations in a computer to get to the answer. And so this is how most of my work gets done, running these kinds of simulations or models on a big supercomputer like this. So this is the basics behind what we're trying to do. We're trying to solve the force of gravity between lots and lots of different points. So if for example, we could do the Nbody problem for everyone in this room, but we'd still need to use a computer like that in order to get it done in a reasonable amount of time. So I said when we have a galaxy like this one, we actually need to use a big supercomputer to do it. So that's just one galaxy. But does anyone know how many galaxies there are in the universe? Back there? 9. It's not too far off. There's probably several billion. So we have something between 9 and several billion galaxies in the universe. And it turns out that if we want to understand, well, we can look at this. So this is our galaxy here. And we're sitting about 20,000 light years out of the center of the galaxy. And when we look into the sky and we look to see where the galaxies are, we can see all kinds of structure here. So this is what we would see if we're looking towards the center of the galaxy. So that's the center of the galaxy there. And if we look up out of the plane of the galaxy, we see all this structure in here. So each of these bright points here correspond to galaxies. So that's what we see from the perspective of the Earth. If, for example, we were like this superhuman and we could sort of step outside of the universe and look down, this is what we see. So the Earth is over here, and this is the depth in the universe. So we can see this structure in here. It's not randomly distributed. You can see it's got a foam-like structure or a web-like structure. And so one of the things that astronomers have tried to figure out is, why do the galaxies in the universe have this web-like structure? You had a question there, quickly?
Yeah, for the last one, where exactly would our solar system be?
Here? So this is from the perspective, well, the solar system is here. So we're looking towards the center of the galaxy. So it turns out that we can have a good stab at the answer. So has anyone seen this picture before? Probably not. Okay. So this picture is an image of the oldest light in the universe that we can see. This light corresponds to light from the universe as it was about 400,000 years after the Big Bang. So that's about 14 billion years ago, 13 billion years ago. So this is extremely old light. And so what this light represents, when the Big Bang happened, the universe was extremely hot. And whereas when we're breathing in fumes from this room, or the gas in this room, the gas in the universe, as it was back then, was very, very different. It was so hot that the gas was ripped apart. Who knows what atoms are made of? Do you know? Exactly. So the universe was so hot that the atoms were ripped apart. So the protons and the neutrons were able to stick together because they're very strongly bound together. But the electrons, every time an electron was bound to the proton and the neutron, all of a sudden some very energetic particle, it might be an X-ray or it might be some very energetic bit of light, would come along and kick the electron out. So the universe was so hot that you didn't have normal gas like we have in this room. You actually had something called a plasma. It was actually more like the surface of the sun. Now, as the universe aged, as it got older and older, it got bigger and bigger because the universe is expanding. And after a while, the heat radiation within the universe had cooled enough that atoms could start to recombine and form the atoms that we see today. And so what we're seeing here is what's left over from this very early cooling of the universe. So prior to this time, the universe was a bit like the surface of the sun. It was a hot plasma. And after this time, it was full of gas, like the atoms that we have in this room. And so what we're seeing is the light that's left over, the light that was emitted when that happened. Now you can see that this light is quite mottled. You've got hot points here, the things that are red, and cool points, the things that are blue. And what that's telling us is that the universe wasn't nice and smooth. There was some structure in there. It was a bit like when we go down to the beach and we look at the waves on the ocean, there were ripples in there. And so rather than ripples in water, this was actually ripples in something called dark matter. And so who's heard of dark matter before? A few people, yeah. So it turns out that the stuff that we're made of, you know, we're very, very special in some ways because there's so little of it compared to dark matter. Most of the matter in the universe is something very exotic. We don't know what it is, and that's one of the things that astronomers and people who work in particle physics are spending a lot of time to figure out. What is this dark matter? But we know from all the indirect evidence that we have that most of the matter in the universe is made up of dark matter. So about 80% of the universe is in the form of dark matter. And this is important because it's this dark matter that's giving rise to this very mottled structure that we're seeing here. And this is what's giving rise to all the galaxies that we see today. So if we go back 14 billion years, there's nothing in the universe. It's very, very smooth, save for these very small deviations. And these small deviations are the seeds of the galaxies that we see today. I'll quickly go through why we think there is so much of this dark matter out there. So we've had evidence for dark matter for about 80 years at this point. And the first evidence we had came from this guy here, a guy called Fritz Zwicky, who went away and he looked at a massive cluster of galaxies. He was looking at this cluster over here. This is the Coma cluster. So this is a cluster of about 1,000 galaxies. And so what he did, he said, when I look at this cluster of galaxies, it looks like they're sticking together. It looks like they're gravitationally bound. And what that means is that if they're gravitationally bound, they're not flying off into the distance. And he was able to say, well, I should be able to figure out how much matter is in this galaxy cluster. And the way I can do that is by looking at how much light there is. And if I know how much light there is, that'll tell me something about how much mass there is likely to be in there. And if I know how much mass there is, I can kind of figure out how heavy the cluster is. But the other thing I can do is I can go away and I can figure out how quickly these galaxies are moving. Now, if they're moving too quickly, they'll be moving too quickly to remain gravitationally bound. They can sort of like explode. But because I'm not seeing them exploding, I know that there has to be enough mass in there to keep them together. And so when he went away and did that calculation, he found that there appeared to be too little mass to explain why they were hanging together. The galaxies were zipping around far too quickly. Why weren't they flying off in all directions? And the reason for that is, well, we think dark matter. There's a lot more matter in this galaxy cluster than we can actually see. So Zwicky did this back in the 1930s just by looking at the motions of galaxies. Since then, people have been able to use satellites and looking at X-rays from these massive galaxy clusters, a bit like what we find when we go to the hospital and the doctor has to see what's happened to your arm, if it's broken or not. And so we've been able to use these X-rays to try and say, well, there's a lot of hot gas in there. And the fact that the hot gas hasn't escaped and disappeared tells us that there must be a lot more mass in the galaxy cluster than we can see. So we've known for a long time that there's probably dark matter in these galaxy clusters. We've also known for quite a while, not as long as in Zwicky's case, but we've known for quite a while, probably about 40 years now, that there's dark matter around galaxies. So this galaxy here, this is the Andromeda galaxy. It's very like our own galaxy. And we can actually estimate how much dark matter there's likely to be in there as well. So back in the 1970s, this lady here, Vera Rubin, and subsequently this guy here called Mort Roberts, they went away and they said, okay, how can we figure out how much mass there is within the galaxy here? What we can do is we can look at how quickly the stars are moving around the center of the galaxy. And as I step further outwards, I might expect the speeds of these stars to drop off, like this red line here. And that's what we see in the solar system. When we look at the orbital speeds of the planets in the solar system, we find that the planets in the outer parts are moving more slowly relative to the planets in the inner parts. And so you can do the same thing with the stars, and you can say, well, I might expect the stars out here to be moving more slowly than the stars in here. But when they went away and made those measurements, they didn't find that. They found something that looked more like that white curve. And so what that was telling us that there is a lot more gravity, in a sense, in the system than we can observe. And this was the strongest evidence at that point for something called dark matter. Now, since then, there's a lot more evidence for this dark matter. So, for example, this is a massive cluster of galaxies. So there's about 1,000 galaxies in here. And we can see these streaks. Now, these streaks correspond to lensed galaxies. So these are very distant galaxies behind the cluster. And as the light comes towards us, it gets streaked out and lensed like this. Does anybody know who this person up here is? Exactly. So, who knows anything about Einstein? Or what do you know about Einstein? Oh, sorry. You know something already. Anybody know anything else? Well, you tell me what you know. Can you tell me what you know about Einstein then?
Albert Einstein was one of the smartest men in the world.
Yeah. That's true.
He figured out flying machines and identify by and he also figured out how light is distorted by going through objects.
Yeah, that's true. So Einstein, so we had Newton coming up with this theory of gravity about 400 years ago, and then Einstein came along about 100 years ago and came up with a new theory of gravity that built on the work that Newton had done. So exactly as you said, he came up with this new theory of gravity. So Einstein said, when we have gravity, when we have this force of gravity between me and you and me and you and me and you, really what's happening is that there's something called space-time that we all occupy. So you can imagine it like the surface of a trampoline, and you're putting a bowling ball in the middle, and you can see that the bowling ball causes the trampoline material to indent. And Einstein had the same idea about what's giving rise to gravity. So basically, when we have something like over here, this might be a galaxy cluster. Einstein was saying, well, the presence of the galaxy cluster, the mass of the galaxy cluster is causing space-time to bend and warp. And so what happens is that we have light from a distant galaxy, and it's coming towards us. Now, if it was coming along the surface of the trampoline material, say, away, in a sense that was away from the bowling ball, it would just continue to follow a straight line. But the presence of the bowling ball, or say the presence of the galaxy cluster, causes the light to get warped, and it starts to follow the sheet. And so this is what's giving rise to this lensing effect. So this prediction of Einstein is actually very, very useful for telling us about this dark matter. So that's another very strong piece of evidence for this dark matter. Now, perhaps the strongest piece of evidence comes from something like this. This is a massive collision or a crash between two massive clusters of galaxies. So you can see this is one cluster over here, and this is the other cluster over there. So you can see there's about 1,000 galaxies over here and maybe a few hundred galaxies over there. We can also see this red material here, and that corresponds to hot gas within these galaxy clusters. So what's happened is you've had gas and galaxies within these galaxy clusters smashing together. Now, when galaxies smash together, mostly the space in between the galaxies is empty, so they just pass through each other. So that's why you've got galaxies over there and galaxies over there. But when you have hot gas, when it smashes, it stops, and it clumps in the middle. And so we're able to see this effect when we look at this. So what we're doing here, what astronomers have done here, is they've looked at the hot gas, colored red. They've looked at where the galaxies are, and you can see it's kind of slightly tinged blue. Now, what they've been doing here is they've used this technique that Einstein came up with, this so-called gravitational lensing technique, to see where the mass is. So you can see there's a lot of mass over here and over here. And most of the mass is over here where the galaxies are. And this is where the dark matter is. So this is another very strong piece of evidence for this dark matter. So we know that most of the matter in the universe is in the form of a dark matter that's quite unlike the stuff that we're made of. And when we look at the structure of the universe in these very large scales, we see something like this. So we can take that picture that we had earlier of the cosmic or the matter as it was in the very early universe, and we can use a supercomputer to see what it looks like, it should look like at the present day. And this is what we see. So this is what the universe would look like on a very, very large scale. So this is basically a measure of the universe about 10 billion light years across. So this is the universe on a very, very large scale. And you can see it isn't randomly distributed. It's got this very web-like structure. And we expect to find galaxies where the regions are, where you're seeing the web cross each other. So you can see there there are these regions that are empty, which we call voids. And then there are these thread-like filaments, or things that we call filaments here. And then we have these things called knots. And in these knots, that's where we expect to find galaxies. So we would expect galaxies not to be uniformly distributed throughout the universe. We would expect it to have this kind of structure. And we can take those results and compare them to what we actually observe. So this is similar to the plot or this is similar to the picture I showed earlier of the distribution of galaxies from something called the 2DF Galaxy Redshift Survey, something that was carried out in Australia. This thing here is from the CFA survey, and the one at the top is from the Sloan. So these are recent surveys of galaxies where astronomers have gone out and they measure the positions of all these galaxies and they've plotted them to show how they are relative to the position of the Earth. And we can do the same thing with the results from these supercomputer simulations, and we can compare the two. So this is what we see when we take something like that Millennium simulation, or that simulation of the universe on large scales that I showed earlier, this one here. And when we look at the structure that we expect to see, this is what we get. So we can see that they're pretty similar. So this is a very important way that these simulations are being used to help us understand what's going on with the universe. We can actually understand what's giving rise to the structure of the universe, and it's purely gravity. That's the thing that's driving it. So the stuff that Newton was doing 400 years ago allows us to understand why the universe looks the way it does. So we've talked about how galaxies are distributed on large scales, but we can start to zoom into those scales and we can say, well, let's look at these individual galaxies. So we can see galaxies here and here and here. So these are real galaxies. These are galaxies that people have gone out, astronomers have gone out and used telescopes to observe. And you can see that there's a lot of different kinds of galaxies here. They all have different shapes. And the thing that we want to do is understand why they have those different shapes. And so we find quite often that when we look at galaxies, we might see something like this here. So we can see there are two galaxies that appear to be close together with these big tails or streams of material. And when we zoom in, we can see that there are lots of regions where there are new stars being formed, baby stars, regions where there's lots of dust being formed. And this is very, very interesting. And we want to understand what's happening here. Why do we see this? And again, it turns out that it's gravity that's driving this same force that Newton talked about. We can build computer models of two galaxies and see what happens when we smash them together. And so this is an example of a computer simulation where we have two galaxies that have been thrown together, and we can see that we have these tails, very much like the ones we see over here. And these tails are what happens when two galaxies come together and they start to rip stars out. This is what happens when galaxies are being shredded. And this is something that happens all the time in the universe. It was very important for building up our own galaxy, and we can see evidence of it all the time in the local universe. So that's just purely gravity. But there are other cool things that happen when we make galaxies. So this is the galaxy that we saw earlier. This is this nice spiral galaxy, M81. And we know that within M81, there are regions where baby stars are being born. So that's something that we can see. And when those baby stars are born, you'll have all kinds of masses of stars. You'll have stars that are very like our own sun. You'll have stars that are much less massive than the sun that will live for a very long time. And you'll have stars that are much more massive than the sun that will live for only a few million years. And when those stars, those very massive stars, are alive, they're actually blowing very violent winds the whole time. So that's what we can see up here. And these winds are being blown out into their surroundings and driving gas out of the galaxy. They also fry the gas around those stars. So where we have those stars, because they're producing such energetic radiation, it causes the gas to heat up and dissipate away. And then at the end of their lives, they go through these massive explosions called supernovae. So they get ripped apart in a fraction of a second, and they have big explosions that can stretch many light years across. So this is an individual star that's died, but quite often we find bunches of these stars together. And up in that top left-hand or right-hand corner from where you are, you can see this is a galaxy seen edge on, and you can see that you've had lots and lots of these massive stars die, and they've driven a very violent wind out, so they're kicking gas out of the galaxy up there. You got a question?
How would the fire be able to keep running out there if there's no oxygen for it to run on?
So it's not really a fire. It's basically a blast wave. It's a bit like what happens when you, well, I guess Do you remember the space shuttle?
Yes.
Okay, so you know when the space shuttle is accelerating out of the Earth's atmosphere, and all of a sudden you see basically a shock forming in front of the space shuttle. So it's the same kind of thing. It's driving a shock out into the gas. Yeah?
Also, the stars when they die, they actually might turn into a black hole. You never know.
So that's a very good point. So very, very massive stars can turn into black holes. So these are lots of really cool processes that are going on in galaxies, and these are the kinds of things that we can model in supercomputers. And so if we just go back to here, we know all of these processes were incorporated into this simulation, and when we include them all, we can produce things that look like real galaxies. So it looks like that we can understand pretty well how these different processes affect the galaxies that we see. Okay, so I'll quickly just talk finally about how these are so useful. So Australia is actually very, very good at looking at galaxies, at doing observations of galaxies. And so at the moment there are two very exciting things, both of which are supported by CAASTRO over there. And so one of them is this SAMI Galaxy Survey. And so the idea here is that we're using this telescope here called the AAT, the Anglo-Australian Telescope, which is in New South Wales, to look at distant galaxies. And so this is an example of a real galaxy up here. And what we're able to do is actually look at the structure within the galaxy, and not only the spatial structure, so where the stars are, but also how the stars are moving. And so you can see this clumpiness over here, and this would correspond to regions that are moving away. The other thing, or moving towards us or away from us, so we can actually start to build up a model of the galaxy based on how things are moving, not only based on where things are, but how they're also moving. The other thing that we can also do is look at the light and look at special things. When we look at light, we can break it into its spectral lines. We can pass it through a prism, and we can start to look at red, green, blue. We can start to do the same thing with the light from the galaxy and tell lots of really interesting things about how stars are forming within that galaxy. So this particular light up here called H alpha, or it's a particular line from hydrogen, is telling us about how stars are forming. So we can see clumps of stars over here and here and here. These are baby stars that are forming. So this is a very cool survey that's going on at the moment. And the idea is that it'll look at about 3,000 galaxies over the next few years. And because we can build models of these galaxies in supercomputers, we can start to compare the results from the supercomputers with what we actually observe and learn a lot more about what's going on. And then finally, this is the last slide, and then you can ask me lots of questions if you have any. There's something that we're planning to working towards in Western Australia, and actually across Australia as well. It's called a square kilometre array. So this is a $1 billion telescope that's going to be built in the outback. Some of it's going to be built in the outback of Western Australia. Some of it will be built in the desert in South Africa. And the idea is that it's going to look at not just thousands of galaxies, but billions of galaxies. And it'll be able to look at galaxies as they were back over several billion years of cosmic time. So we'll actually be able to see what's happening in the very, very early universe. So these are the different kinds of antennae. So they're quite different from the telescopes that are outside there. Rather than looking at optical lights or lights like we can see in here, they're looking at radio waves. And radio waves are very interesting because this is a picture of the Andromeda Galaxy over here that you've probably seen before. This is what the Andromeda Galaxy looks like when we look at it in radio waves, when we're looking at the neutral hydrogen in that galaxy. And this is the material that is forming stars within this galaxy. So this is what happens. This is what the galaxy would look like before stars have formed. And so by doing that, we can actually start to get a new insight into how galaxies are forming. We haven't been able to do this in a lot of detail before, but in the next 10 years, we'll be able to do this for billions of galaxies and learn a lot more about how galaxies are forming. And again, we can use the results from supercomputer simulations to really tell us a lot more about this process. So that's it. Any questions? Yeah?
Who's paying for that?
So there's it's a consortium of about 12 countries. So it's about,
It's government funded.
basically it's taxpayer funded, yeah.
Cool, excellent.
So yeah, some of your dollars are actually paying for
Yeah,
it.
I'm good with that.
Yeah. Any other questions? Yeah.
Before you said dark energy, what is that?
Well, that's a good question. So that's another big doozy. We don't really know what it is, but what we do know is that it's causing the actual universe that we see today to expand. So and the expansion is accelerating. So basically, in the next few billion years, the universe will continue to expand, and it'll start to get, the expansion rate will continue to increase, and by the end, we won't be able to see any other galaxies around us in a few billion years. The universe will be cold and dead. Any other questions? Yep.
My son really wants to know about meteorites and whether they're on fire. What was asking about fire.
Okay. So, well, basically, what meteorites are, they're dust in the solar system. So, have you ever seen a comet, or do you know what a comet is? It's like a big ball of, it's a big snowball that's orbiting around the sun. But it's not just ice, it's also dust. And as it orbits around, it gets heated up by the sun. And as it moves along its orbit, it leaves bits of dust. Now, so what happens then, as the Earth is orbiting around the sun, every so often it will cross this path of the comet where that dust is. And as this dust enters the atmosphere, can you rub your hands like that? Rub them? Can you do it? Do you notice something? It's getting hot, isn't it? It's friction. So as this dust passes through the atmosphere, it's basically getting heated up by the atmosphere, and that's what causes it to kind of set fire. Okay? And that's what we see as a meteorite, or a meteor. Yeah?
In WA,
Yeah.
where roughly about?
Do you know where Geraldton is?
Pardon?
Do you know where Geraldton is?
Yeah.
So it's probably a few hours drive inland to the northeast.
More in the vicinity of Giles Stone?
I'm not. It's Boulardi. Do you know where Boulardi is? Or do you know where Boulardi is?
The Giles meteorology station.
Oh right, okay. I don't know. When I've been there before, we've flown into this cattle station, and it's probably about a 20-kilometre drive from there. So. I can find it on Google Maps for you later if that helps. Yeah.
This on the top right-hand corner of the slide, the Andromeda galaxy.
Yeah.
Is there actually a black hole in the centre?
No, it's just because it's gas. When you're looking at gas, and there tends to be like a deficit of gas in the central regions. It's because normally the gas is so dense in there that it prefers to form stars. So you'll form a lot of stars, and that'll remove gas. Any more questions? Yep. Could a solar flare? I don't think it would destroy Earth, but it would cause havoc with communications and the atmosphere. Yep.
Is there a possible fact that the work of electrons these are sun turning into a red giant?
Well, it will, because as it turns into a red giant, its atmosphere expands, and it'll probably expand out to about the orbit of Mars or just beyond that. So, yeah, but that's 5 billion years' time, so nothing to worry about. Yeah.
Well, when the sun dies, it actually turns into a big hot ball or something?
So it'll become a red giant. It'll go through a red giant phase.
Yeah,
And
big red.
yeah, so it becomes very big. So does anybody know what Betelgeuse is? Or does anybody know where Orion is? Have you ever looked at Orion?
No.
So Orion's
When you look up in the sky, you see those three stars that are like sort of
his belt. Yeah.
Oh, yeah.
So, but if you look at his shoulder, there's a big red star there. That's called Betelgeuse. Now, Betelgeuse is an example of a red giant. That probably extends out beyond the orbit of. If you put Betelgeuse in the solar system, it would extend out beyond the orbit of Mars. So what happens then? So it just keeps expanding and expanding, and eventually the atmosphere will just dissipate away, and you'll get something that looks like a planetary nebula. That's what we call them. And in the middle, there'll be a star called a white dwarf, which is basically a big diamond, and that's about the size of the Earth.
That's it.
Yep.
I'd like everybody to thank Professor Powell for coming into our lecture. He's come all the way from Western Australia. And those of you who've got those little balls as prizes, yeah, you did really well. There's also lots of extra stuff supplied by CAASTRO. If you'd like to find out more about what CAASTRO does, apart from just reading their posters,
They've got some little booklets, they've got some lovely slap bands if you like that, and all those other things that kids like. And some fridge magnets, so go over and help yourself with some of that
And
stuff.
if you do want a ball, you've got to come and ask me a question.